All telecommunication systems are expressed mathematically as an equation. Here you can see some products and some addition of various signals. And these equations are expressed as block diagrams. So we can visualize the products and the additions, and there's some oscillators, etc., creating a QPSK signal. And these block diagrams can be implemented by individual hardware circuits, circuit cards, where each circuit card is a mathematical function. Example, a single card for a multiply, for an oscillator, for a phase shifter, or for the addition. This is called the block diagram method, and it allows you to create real electrical signal replicas of the mathematics. And all we ever do in telecommunications is manipulate either the amplitude, the phase, or the frequency of an RF signal. So for amplitude modulation, you can see here that we are only manipulating the amplitude of a single carrier. For phase modulation, we have created a second RF carrier with a phase shift of 90 degrees. So we find that by manipulating two orthogonal RF carriers, sine and cosine, by two driver signals known as I and Q in phase and quadrature, and adding the products of those together, we can create a great variety of modulated signals. Mathematically and experimentally, we can find that the average value of a number of sinusoid or cosine waves equals 0. This is insight 1. Also, we'll find that the integral number of products of any sine or cosines by each other equals 0. So multiplying sine by cosine's harmonics will give 0. The third insight is the average value of an integral number of sine by its own harmonics equals 0. And finally, one that's different, the average value of the integral number of products of a sinusoid by itself yields a non-zero value. So finally, we can see that sinusoids and cosines are independent of each other unless they are the exact same frequency and phase. This insight number 4 is the basis for orthogonality and the ability to extract frequencies in an FFT. Using a combination of independent circuit cards which implement multiplication and addition and other mathematical functions, we're able to build the IQ modulator that we have been discussing earlier. So within GNU Radio, we're able to manipulate the amplitude of the in-phase and quadrature signals, thus giving a resultant signal with a variable amplitude and variable and fully controllable phase. The phasor representation is very helpful. It shows a single frequency and shows the phase and amplitude of that particular component. So for AM, you can see that the component's phase will remain static and its amplitude is manipulated. For phase modulation, you can see that the phase of the phasor is manipulated by changing the I and Q components to create a resultant, which is the new phase modulated vector. Here we take a look at creating FM with GNU Radio. There's an important block is the FM modulator block, which outputs a complex signal, which is then split into two floats. Each one of those floats is the I and the Q signal respectively, which are shown on the right as the red and blue dotted signal. Notice how complex they are relative to AM or PM. This is because they need to take into consideration the integration process that is involved in creating FM. If we dig into the code used to create FM in LabVIEW, we can see that integration is involved, and also the final stage is the conversion of a polar representation into a complex INQ representation. So here we can see a complete transmission system where we have an IQ modulator at the transmitter and an IQ demodulator at the receiver. An example of IQ modulation is with multi-level schemes where the I and Q signals respectively modulate in the horizontal and vertical axis, otherwise known as the in-phase and the quadrature axis relating to the cosine and the sine RF carrier. In this presentation, we have briefly covered how the trigonometric identity nature of sinusoids allows us to extract signals from more complex signals, and the phasor representation of I and Q signals allows us to understand more easily what is happening to the carrier.